Good afternoon. It's Sunday here in Brussels, and I always say it's going to be like the last video, but I always find something to talk about. Um, I'm doing this video a little bit because, unfortunately, a previous video was surprise, taken from my YouTube channel because apparently I used references to Richard Feynman's lectures a bit too liberal. It's very surprising, but yeah, it's a lessons learned. I'm not going to do that anymore. This lecture is not about the topics that I discussed in the lecture that got taken off my channel. That was really a bit of a commentary on, what Feynman had right and what he got wrong. I want to do here something on that hopefully will serve a bit as background to previous lectures, and which I talk a lot about how everything is made up of charges and fields, and how particles like electrons and protons have a structure that revolves around an oscillating charge inside of them. Fields is a funny concept. But it's one that hopefully will become a bit more clear in this lecture. There are basically two laws, grand laws out of classical physics, and the one is charge conservation, and the other one is energy conservation. And the big discussion is always sort of are these global conservation laws, or are these also valid locally? Out of Maxwell's equations, it's quite clear that both the charge conservation law and the energy conservation law must also hold locally. The question is then how exactly, what is the interplay between fields and particles, I would say, or between charges and fields? You will immediately say, yeah, we have matter, antimatter, pair creation and destruction. I'm going to talk about that later. Just let's go for low energy physics now, as they call it, and write down the charge conservation law, which is written down here. The divergence of the current vector must be equal to minus the time rate of change of the charge density. Rho is the charge density. We have the time derivative of the charge density in regard to time is the time rate of change of the charge density, and that's minus the divergence, which, as you know, is sort of the flow in and out of a point or an area of the current. Energy conservation is same easy expression, but not so easy this time because we're going to put it as an energy conservation law relating to field energy density. And you will say in a moment, what is field energy? It's different from the energy of a proton or an electron. It's really the energy that's in the field. And this concept will probably help you to understand why energy is in principle a quantity which is not associated with a direction. Energy is just energy, doesn't flow in this or that direction, but energy density does flow in and out of a region, just like charge can flow in and out of a region. So we have a similar expression here. U, field energy density, which increases or decreases with time in a certain area, and then if that happens, there must be an energy flux away from that region, and that's captured by the divergence of what is known as Poynting's vector. Poynting was a British physicist. Umov was a Russian who was working on the same things and around the same time, but Poynting ran away with the prize of inventing Poynting's vector. Of course, we know all energy is electromagnetic. At least that's what I think. But then what's energy then really? If it's electromagnetic, we know, but energy is basically in its usual definition, it's a force that works over some distance, and it works on what? It works on a charge. So the unit of energy is 1 Newton meter. We have more energy if the force is larger and if the force is expended over a longer distance, not necessarily time. When you involve time, energy expended per second, then you have the concept of power, which is a very difficult, well, not very difficult, but a different concept than energy. So, but here we're discussing field energy, and fields are, well, they are related to forces, but they're not like forces. A force acts on a charge, as said. Photons don't carry charge. Fields become a force when they act on a charge. But so the concept of field basically abstracts away from the idea of a charge, and that's reflected in the physical dimension of the electric field vector and also of the magnetic field vector. It's Newton, the unit of a force, per unit charge, and then it depends if you have a certain electric field, how much charge is there. If we have a lot of charge, the electric force will be very big. Same for the magnetic force. If there's a lot of charge moving, because we know that the magnetic force is kind of special, then the force the magnetic force will be very big. I want to say a few words here on, electric and magnetic force. We know both are relative, depends on your reference frame, what you see as being the electric force and the field force. And we know there is more fundamental realities underneath that, and that's the scalar potential and the vector potential. And when we have the scalar potential and the vector potential, both are a full vector, then we can derive the electric and the magnetic field vectors. Why do we say it's more fundamental? Well, with an electric field vector, you have 6 numbers for each point x, y, z in space. You have a component of the electric field in the x, y, and z direction. So you combine 2 times, or I would say 3 mathematical dimensions. I talked about that before, so I'm not going to repeat myself. But here, we like to think it's more intuitive in electric and field and magnetic field vectors, and so that's what we're going to do. We know the Lorentz force, again, to just stress the point that the real thing is the force on a charge, and it's always the charge times the electric field vector, which is the force per charge. So, and for the magnetic field, we know we have this special construction that when there is a magnetic force, magnetic field, then the amount of charge will determine the velocity that this charge is going to, the acceleration that this charge is going to get, and the velocity as a result, because of the magnetic field working on an actual charge. I put here a few other things that may or may not be useful. Again, abstracting away from charges, we have only 2 out of 4 Maxwell's equations that are relevant, and that's this swirl around a point, the curl of the electric field, which is given by the time rate of change of the magnetic field vector. And also, when there is a magnetic curl, some circulation of the magnetic field, then we know it will generate an electric field given by 1 over c squared times the time rate of change of that electric field. We may write it in terms of the magnetic and electric field constant. We can also, and I find it very useful, write it as sort of using the imaginary unit to show that the magnetic field vector is always perpendicular in a very specific way, applying all the conventions to the electric field vector. So we rotate the electric field vector by 90 degrees, divided by c, and then we get the magnetic field. Why is all this relevant? Is just to show that what I show here a bit, you have these nice pictures on Wikipedia or in Feynman's lectures of circularly polarized photons and linearly polarized. Linearly polarized goes to a thing and we only keep the one component of the electric field. And we always forget about the magnetic field vector. And why? Well, because it's smaller. It's 1 over c. It's very minute. Well, that depends on your scale. If we take a different reference frame where we sort of define the light second as a distance unit, we write it as m prime. You'll say that's not a different reference frame. Well, it kind of is. We sort of stretch, if you think of a time and a distance axis, we change the unit of the distance axis, and that gives us a bit of a different reference frame. So then we have that the speed of light is equal to 1 normally, expressed in terms of light seconds per second. And then it's kind of surprising when mathematically the magnitude of your magnetic and electric field vector will be just one of the same. So you should not think in terms of magnetic and electric force being and fields being more or less important. They're two aspects of one of the same thing. And again, we see that when we write out the Lorentz force formula. What changes is that this velocity, when we choose the light second as a distance unit, will vary between 0 and 1 instead of between 0 and c, the speed of light. So that's all kind of simple. So I do refer, I hope that's not seen as a copyright infraction, but sort of in Feynman, his second volume, lecture 27, you have a derivation of these results. What is that field energy density and what is that Poynting vector? It turns out that it's 1.5 times the electric field vector squared, the magnetic field vector squared, times a constant of proportionality, which for the electric field vector is the electric constant, and for the magnetic vector is the magnetic constant. I quickly gonna show that since the 2000, because that's often forgotten when you read sort of these Wikipedia articles, that electric, magnetic, and the speed of light are co-defined and can sort of be derived from more fundamental, the real fundamental natures of constant, Planck's quantum of action h, the unit charge, and the fine structure constant. The 2019 revision has really a lot of answers to what in Wikipedia are touted still as a being big mysteries to be solved. I will quickly show the precise formulas in a few slides I used for my previous lecture. They are these. Always remember that. Since the 2019 revision of SI units, the fine structure constant, magnetic and electric constant are co-defined, so to speak. The relative uncertainty in their measurement is therefore the same. Let me go back to these concepts. Energy sort of having some kind of direction, and energy flux being given by the Poynting vector. What does it mean? Well, this is a mathematical formula, which again you can go to textbooks. We get that sort of flux from a cross product from the electric and magnetic field vector divided to get its magnitude by the magnetic constant, which you can write in terms of C, or the electric constant, or if you really want to be very fundamental, in terms of the fine structure constant H, unit charge, and C. The point to reflect about here is the physical dimensions of these two concepts, and then they become not so mysterious anymore. This symbol, this bracket, right, means we take the physical dimension of the energy density. If you do that, take the formula. The magnetic constant is written in terms of Coulomb squared divided by Newton meter times the square of the physical dimension of the electric field vector, which is Newton square, divided by Coulomb square. We do the same thing, adding that c square for the magnetic field vector, and we get Newton meter. You will say, what is this? Well, it becomes a little bit clearer when you multiply with m divided by m, and then you get indeed an energy joule per unit area. Not a cube, but a unit area, two-dimensional, which makes sense if you talk about energy flows through a surface. For Poynting's vector, you get the same. You effectively get what we wrote here. It should be a change in the energy density. So that energy density is written in terms of Joule divided by meter square. I can't clean up my presentation anymore. And it's divided by seconds. So it's indeed a time rate of change of the energy density. So we do get a flow of some energy per unit area per second. You will say that's Chinese, and how does it work? Well, there again, I'm gonna point you to Feynman or other textbooks. The charging of a capacitor, where you have two plates with opposite charges, negative, one positively charged, one negatively charged, and you charge that capacitor by moving even more electrons, let's say, from one plate to another. So you're going to charge that capacitor, and the whole charge stays neutral, but the energy of that capacitor is going to change. And you can analyze that in terms of this energy flow of the fields. And that's an analysis which is otherwise difficult to do, because if you charge a capacitor, its energy is going to increase. And how does it work? The charge capacitor as a whole is neutral. We have positive and negative charge on the two sides with two plates and then an insulator in between. But still the energy increases. So how does that work? That can only be explained by indeed looking at an analysis in terms of this field energy density that changes. A solenoid or a simple wire carrying a current can be analyzed very conventionally. But analyzing them in terms of these energy densities and energy flows makes a lot more sense. I'm going to conclude to talk about field momentum, because we talked about field energy, and as you can see, it's a bit of a different beast. Energy is probably one of the simplest and at the same time most confusing concepts in physics. So field momentum, you associate momentum with a particle, right? A certain particle has a momentum p, and it's a vector. It's a product of its mass, which is a directionless concept, times its velocity, which has a direction. So the momentum will be in a certain direction. If the velocity vector is here, the momentum vector will also be in that direction. Mass is energy divided by c squared. We know that from Einstein's formula. In my working papers on ResearchGate, which I will reference in a moment, you can see that energy basically in a particle energy is a charge in motion. It's a charged oscillation. And then we have the difference between an electron and a proton and whatever. But so how do we translate to the flow or a concept of momentum for fields. Well, we're going to start by defining momentum density in a very simple way. We have this flow of energy density in the field, and we have this very easy concept of momentum, where basically momentum is a velocity, but multiplied by the mass. We always know the mass is proportional to the energy, and the constant of proportionality is 1 over c squared. So very much like this equation, m is e squared divided by c squared, we think, if you talk about energy flow rather than energy, which we have here, Poynting's vector is an energy flow, then maybe we have a momentum flow vector, g, which should be equal to 1 over c squared. This is not very intuitive. To make it more intuitive, I would recommend then to look again to Feynman. I hope this doesn't get scrapped. It's a liberal reference. I just give the page numbers 27 to 29 in volume 2. Sorry, pages 9 to 11 from chapter 27. And that's a very funny example of a closed car, and somebody sitting in the front, and then has how do you call it? Switches on a beam of light towards the back of the car, and so that beam of light is gonna give that car a very small acceleration, because there is momentum in that energy of the light he fires. There's a recoil momentum, and the car then moves, and then it hits the wall of that car, and the car stops again. And it's a very, very interesting argument where basically when you read it, then you say like, okay, yeah, Einstein was right. And paraphrasing a book, Einstein's Unfinished Revolution, I think Einstein's revolution is finished. So I'm gonna leave it at that for a Sunday, and this will probably not help very much. Look at previous lectures, but the point to note is that there's really not much of a mystery left. I had planned to talk about the real electron diffraction experiment that was carried out in 2012, and to explain that the real interesting thing is actually what happens on the edges of slits, and that's just an airy pattern rather than the way how Feynman describes it. It's all quite straightforward. This is the airy pattern again for a laser. Things like this, this is what drove me. How can we explain these diffraction patterns? It is not a rocket science. Compton scattering, once you start defining what a photon really is and defining what an electron really is, a point-like charge, really a point-like charge, it has some dimension which explains the fine structure constant, going around and around and around some center, and then you have formulas that when you push them to the limit make sense, that they don't. But it's all there. There is no mystery. I have one on, especially here with these diffraction patterns, the importance of resonance phenomena. I refer to my reading Feynman blog, which got mutilated by the same guy who thinks I'm using Feynman as lectures too liberally to illustrate a point, or to note that something he doesn't go all the way in his reasoning. But Modes and Music is one post from 2015. Nice to read, not too much math. For the tougher stuff, check out my ResearchGate page, Jean-Louis Van Bella on ResearchGate. And that will be it. For me, it's been very fascinating to the adventure of the last 10 years. I always say it doesn't take any away of the magic. These beautiful, beautiful pictures here, a sunset, and how the colors they diffract are reflected on a water surface and give this beautiful image. It's not because you understand. I would say scientifically, you never get sort of like it's too complicated to get the full picture in your head immediately, but intuitively, that it makes sense that these patterns are there not because of some mystery, because of quantum mechanical phenomena, which can be perfectly explained, and indeed an uncertainty, which is not a metaphysical uncertainty, but has to do with, velocities and high velocities, speed of light, and the fact that we never quite know where a photon is exactly. A photon is point-like. That sort of doesn't make it any less pretty, and that's my positive message. And like what Feynman said at the end of his life, that dying is very boring, so I wouldn't like to do it again. When I think about that, I think life is so exciting, and you surely want to live again, and that's why dying can not be boring, because you do not want to die. You want to keep exploring and have fun with all these things, thinking it through for yourself. Um, that was a short lecture, 25 minutes. I hope you enjoyed it. Um, if not, then it's the same. Keep thinking.